Welcome, y'all. We got another different kind of interesting question here with magnetic fields and moving charges. We have a wire that's running straight up and down out of the paper. It has current flowing through it. The current is flowing upwards in the wire. And then we have another particle over here which has a positive charge. That particle is also moving upwards parallel to the wire. And so the question that they want us to be able to solve is determine the magnitude and direction of the magnetic force on the particle at this point in space. All right. Now, in order to do that, obviously to be able to figure out what's happening to this particle right here, we're going to need to be able to figure out what the magnetic field is at that location. All right. So the direction of the magnetic field is easy enough. We just use our right hand rule. Remember, we can use our thumb to represent the current going up the wire, and then our fingers represent the magnetic field. And so that I can see in this situation with my thumb going up, my magnetic field is going to go back around the back like that and then come back over forward. So in the place where the particle is, it looks like it should be going around this way, which means here the magnetic field is going to be perpendicular to the velocity, but it should be kind of going in that direction right there. So I now have the direction of the magnetic field as the magnetic field goes around the wire just like that. Okay? We can also get the magnitude. In our AP formula packet right here, we can see that the magnetic field is equal to the magnetic permeability of free space. We got the current and then 2 pi r. So we can put all that together to get our answer. So we've got our mu naught, we've got I, the current, we've got 2 pi, and we've got r. So let's go ahead and put all that together with the information that we have. We do have the magnetic permeability that is given in our formula packet. It is right here somewhere. There he is, vacuum permeability. That is 4 pi times 10 to the negative 7th. Okay, so 4 pi times 10 to the negative 7th times the current. In the problem, it says 3 amps right there, so we'll put that in. Then we'll divide by 2 pi and the r, which is the distance that we are away from the wire, which is that 0.050 meters. So we can calculate that. That's pretty easy there. So we'll just go 4 times pi times, actually I'm not going to use times, I'm going to use the e negative 7. That'll make sure that I keep it all together. We'll multiply by the 3.0. Then we're going to divide by the 2. We're going to divide by the pi. Okay, don't divide by 2 pi because it might divide by 2 and then multiply by pi. It probably depends on your calculator. Honestly, I have no idea. But I'm always trying to be safe with that. So divided by 0.050. So I'm just dividing by each of those things. You can also put all of that in parentheses and just do one division there, and that would solve your problems as well. And of course, I've got a error there. So it doesn't like that. So let's go. See, learn something new every day. It doesn't like that pi e. Still doesn't. You know what? Let's go ahead. We're going to divide the pi out. I got pi on the top. I got this is I don't mind doing this in the video. I think it's important to recognize that sometimes things don't work out the way that we expect them to, and we have to adjust. So I tried the parentheses didn't work. I said, well, let's just get rid of the pi's, and then I had to get rid of the parentheses again, and now I do finally get an answer for the magnetic field, which is 1.2 times 10 to the negative 5th. Sometimes calculators don't do what I expect. You got to figure out what it thinks you're saying and then resolve the issue. So we have a magnetic field 1.2 times 10 to the negative 5th Teslas. And now we are trying to find the magnitude and direction of the force. So the force then we know is equal to QV sine theta B, all of which we have. We have the charge of the particle, which is 6.5 times 10 to the negative 6th. We have the velocity, which is 280 meters per second. And the sign, of course, is still sine of 90, which is going to be 1. And then the magnetic field we just found, which is 1.2 times 10 to the negative fifth. And so we'll multiply that by the 280, and then multiply by the 6.5 times 10 to the negative sixth, and we get 2.18. Looks like I only have 2 sig figs, so 2.2 times 10 to the negative eighth. Now we need to say the velocity is moving this way, the field is that way, and my thumb then is pointing towards the wire. Okay, so velocity is going upwards in the page, right? It's going up there. My field is going kind of into the page that way, and so my thumb ends up pointing directly towards the wire. So that's kind of cool there. Remember that we don't need to look at the magnetic field created by the particle in any of this, right? We know that because it has a charge, it has a magnetic field, and therefore it will interact with the magnetic field created by the current. However, we don't have to find the magnetic field of this because the right-hand rule just allows us to take the motion of the particle and the field created by the other object, and it automatically tells us how it's going to interact with that. Okay, so that's this one. That's kind of a different, neat question dealing with field and velocity and force and the interaction of two fields with each other. So I hope that was helpful. We'll see you next time.